So what if we want to do a 1,4 conjugated addition, but we don't want to use some doubly stabilized anion? We just want to have one of them, right? So we just want to take a regular carbonyl, an aldehyde or a ketone, and then we want to do some kind of conjugate addition, right? So we'll add some base, then we'll add our Michael acceptor or our electrophile, and then we'll do an aqueous workup. And the issue with this one is once we form our enolate, because it has this full-on negative charge, it's too nucleophilic. And we said when you get more nucleophilic, you're going to do direct addition. And so what we're going to end up here is conjugated and direct addition. And so that's not going to produce a good effective yield for us. So is there any way that we can do just regular carbonyls and still do conjugate addition? And of course, if I'm talking about it, the answer is yes. And it's through this Stork enamine synthesis. So basically what we're going to do is we're going to turn our ketone or aldehyde to an enamine, and this enamine is going to be less reactive. And so it'll do the 1,4 addition instead. So for example, we could take our carbonyl, and then we could use a amine that has 2 R groups. The most common one is this 5-membered ring called pyrrolidine. And so we add that, an acid catalyst, and then we can distill away any water that's formed. And then what we've got here is an enamine, which we learned about it later, right? And so you see the difference between the enamine and the enolate. We have no formal negative charge. And so we're less nucleophilic. And since we're less nucleophilic, we're going to disfavor that direct addition and favor that conjugate addition instead. Right, we're less nucleophilic. And then after we do the conjugate addition, we can just hydrolyze our enamine back to the carbonyl. So let's take a look at this. So once you've got your enamine formed, then you add in your alpha beta unsaturated compound. This kicks down. This attacks that position, kick over here, kick over there, and form a carbon-carbon bond. You see, it's the same as an enolate attacking, except instead it's just an enamine. Then our intermediates. We'll end up with this intermediate, and then basically all we do is an aqueous workup. This enamine will be hydrolyzed back to the ketone or aldehyde. And then this enolate will undergo a proton transfer and then keto-enol tautomerization to go back to the aldehyde or the ketone. And then our end product is what we wanted originally, which is just basically a 1,4 addition with a regular carbonyl. And so the overall steps for this, you start off with your carbonyl. Step 1, you turn it into an enamine. Step 2, you add your electrophile. And step 3, you do an aqueous workup to hydrolyze. And there we have yet another powerful carbon-carbon bond formation reaction.